There is a building design so mathematically perfect that it requires 30 to 50% less time to build than a conventional home. Sheds snow loads that would collapse a standard roof and can be assembled by two people with basic hand tools over a single weekend. I am, of course, talking about the A-frame, a structure that ancient builders from the snowy peaks of Japan to the rugged fjords of Scandinavia embraced due to their unrivaled resilience in some of the harshest winter environments on the planet. Yet, despite 60% of Americans living in areas with annual snow, less than 1% live in them, and instead are sold expensive rectangular boxes that leak, rot, and often collapse under these same environmental conditions. We're about to discover the epic origins of the A-frame, the structural physics that make it the ultimate winter dwelling, and the reasons why most people will never live in one. Let's dive in. In the remote mountain villages of Japan's Sho River Valley, the Edo period gave birth to the Gassho-zukuri, a name that translates directly as constructed like hands in prayer. These structures were a direct engineering response to annual snowfall accumulations of up to 36 feet, among the heaviest recorded anywhere in the world, and a load that would collapse a standard rectangular roof in a single season. The Gassho-zukuri solved this problem with a roof pitched between 60 and 70 degrees, steep enough that snow slid free before reaching a weight the structure could not carry. But the genius of these structures went far beyond the roof geometry. Japanese builders did not use nails, which rust and snap under sustained tension and exposure. Instead, the primary frame was bound using complex timber joinery, secured with hemp rope, a system called sasu. This created a semi-rigid frame that behaved very differently under load than any nail-based construction. During the region's frequent earthquakes, the triangular geometry distributed the energy through the frame, while the hemp lashings allowed the building to flex rather than resist until it fractured. The result was a structure engineered simultaneously to withstand vertical snow loads and lateral seismic forces. 6,000 miles away, the Maori of Aotearoa were applying the same geometric logic to their communal meeting houses. Like the Gassho-zukuri, the Wairanui was designed to withstand the region's frequent earthquakes. The structural members were bound together using a complex rope lashing technique called mimiro, which allowed the frame to shift and flex during seismic events. The form crossed into the modern era of American architecture in 1934, when Austrian-American architect Rudolf Schindler designed the Bonatti cabin in Lake Arrowhead, California. Here, he utilized the A-frame's steep triangular roofline to create a high-volume interior from a minimal material budget. But the broader shift came 20 years later, when the San Francisco firm Campbell and Wong introduced the Leisure House at the 1951 Arts Festival. John Carden Campbell fixed the building's dimensions to the standard width of a 4x8 plywood sheet, eliminating material waste and reducing the build process to something a family could manage without professional contractors or mortgages. Soon after, the pre-cut kits began appearing in department stores at a price of just $5,000, making the A-frame a viable DIY holiday structure for the American middle class. By the mid-1950s, the A-frame had become a cultural phenomenon. Andrew Geller's Elizabeth Reese House on Long Island was featured in the New York Times in 1957 and marketed as a budget playhouse. The A-frame's golden age ran from roughly 1955 through the 1970s, driven by rising disposable income and a new appetite for informal, owner-built retreats. But if you want to understand the structural advantage an A-frame offers, you first need to understand the weakness it eliminates. In a conventional timber frame house, the structure is a series of separate elements connected at joints. The roof sits on top of the wall's top plate, and the wall sits on the floor, both of which are held together by gravity and metal fasteners. And under extreme loading, whether from wind uplift, heavy snow, or seismic force, failure almost always begins at these joints. But the A-frame eliminates that joint entirely. Instead, the rafters run in one continuous structure, acting as both the wall and the roof simultaneously. This creates a continuous load path, in which a force arriving at any point in the structure travels directly to the foundation, eliminating the area of weakness between the roof and the walls. But the geometry itself also adds a second structural property that conventional construction cannot replicate. The triangle is the only geometric shape that cannot be deformed without changing the length of at least one side. A conventional rectangular frame pushed at the corner collapses into a diamond shape. But a triangular frame, on the other hand, will stay a triangle until the material itself fails. So by maintaining a roof pitch of 60 degrees or higher, the A-frame converts the downward force of snow and the lateral force of wind into compression along the rafter, directing it straight into the foundation. This deflection creates a downward pressure component that pushes the structure tighter into its foundation, meaning the harder the wind blows or the more snow that falls on it, the more firmly the building is held down. And this structural efficiency also has a direct consequence on the ease of assembly. Because the A-frame eliminates the distinction between wall and roof, it requires 30 to 50% less time to frame than a conventional structure of equivalent floor area. A small A-frame kit can be assembled by 2 people with basic hand tools in a matter of days. The framing cost for a comparable structure runs between $15,000 and $35,000, against $25,000 to $45,000 for a conventional timber frame. And that 60-degree roof pitch carries one last advantage that traditional box homes can't compete with. It is close to the optimal angle for solar panel efficiency at northern latitudes during winter months, when the sun is low in the sky and energy demand is highest. The entire south-facing roof surface of an A-frame is effectively a pre-engineered solar rack. The case for the A-frame has been proven over centuries of performance in extreme environments and decades of modern construction observations. On a cost basis, an A-frame often incurs less material and labor costs. An A-frame kit can be built for under $150 per square foot compared to a conventional custom home, which runs between $300 and $400 per square foot before finishing. And because the roof and walls are the same, the framing phase alone is 30 to 50% faster. Generally, there are fewer ongoing maintenance costs with these types of structures too. Metal roofing, the standard specification for most A-frames, is a costly upfront investment, but it eliminates the primary maintenance cycle of conventional residential construction. There are no gutters to block, no asphalt shingles to replace on a 10 to 15-year cycle. And in snow performance, the Gassho-zukuri villages of Japan's Sho River Valley have stood for centuries under annual snowfall accumulations that would destroy a conventional structure in a single season. Several of these buildings are now UNESCO World Heritage Sites. So the A-frame costs less to build, frames faster, and performs better under snow and wind loading than the conventional homes it competes with. Why then haven't these become the mainstream construction style in American states with regular snowfall? A handful of minor barriers exist, both bureaucratic and practical. The first barrier is regulatory. The International Residential Code requires a minimum ceiling height of 7 feet and 6 inches for all habitable rooms. In an A-frame, only the central portion of the floor plan meets this requirement. The areas near the sloping walls do not, and cannot be counted toward the legal square footage. Because of this, a developer selling by the square foot loses revenue every time a wall slopes. Essentially, large-scale builders have no financial incentive to construct a structure that reduces their appraised sellable area. Then there are also genuine practical limitations that any honest account of this form must include. The sloping walls mean that standard furniture, bookshelves, wardrobes, and kitchen cabinets cannot sit flush against the perimeter of the building. Conventional storage solutions and ductwork are difficult to integrate without custom fabrication. There's also inherently a lot of wasted floor area in these buildings. Due to the steep slope of the walls, as much as 50% of the floor area can be virtually inaccessible. Loft spaces, for example, while structurally straightforward, only allow full standing height at the center point. In areas that experience regular snowfall through the winter months, the structural benefits outweigh these practical limitations. But when significant snowfall isn't a primary concern, then it's easy to see why these structures haven't become widely adopted. But for those who face regular, harsh winter conditions, the A-frame offers advantages you simply cannot achieve with a traditional box structure. However, some limitations do exist. A-frames face the most resistance in municipalities that apply the International Residential Code strictly and in homeowners association territories that mandate conventional roof pitches and wall materials. Rural unincorporated land in low-code states offers the clearest path, as several states leave building code adoption to individual counties rather than imposing a statewide standard. And within those states, certain counties impose minimal or no residential codes on unincorporated land. Where codes do apply, A-frames are often approvable as accessory dwelling units or leisure structures with lower minimum square footage thresholds than primary residences. Some authorities classify the A-frame as a temporary or recreational structure rather than a permanent dwelling, which can simplify the permitting process significantly. Securing preliminary approval from the local municipality before purchasing land is the single most important step any prospective builder can take. For the structure itself, 3 paths exist at distinct price and complexity levels. The most accessible entry point is a prefabricated CNC kit from established suppliers. Companies such as A-frame and Den Outdoors produce flat-pack systems with factory-machined components, pre-drilled connections, and full assembly documentation. A small kit under 500 square feet can be assembled by 2 people with basic hand tools in a matter of days without specialist construction knowledge. Shell costs run under $150 per square foot, against $300 to $400 for a conventional custom build. For those wanting a permanent, mortgage-eligible result, a custom timber frame by skilled artisans produces the most durable outcome and the greatest design flexibility. This is the most expensive path, but the one most likely to navigate conventional appraisal and financing successfully, particularly if the design incorporates code-compliant ceiling heights throughout the central living area. For off-grid integration, site the structure with the long roof slope facing true south. At 60 degrees of pitch, the surface captures near optimal solar gain during winter months when energy demand is highest. Use the enclosed triangular space near the eaves for battery storage, water tanks, and mechanical systems. A centrally located wood stove in the main living space heats the open volume efficiently. Ground screw foundations, which require no concrete trucks and can be installed on slopes up to 10 degrees, allow siting on terrain that would make conventional foundation work prohibitive. The interior challenge in any A-frame is the sloping wall. Standard furniture and kitchen cabinets are designed for vertical surfaces. The solution used by the most successful A-frame builders is to treat the sloped perimeter as built-in storage from the outset. Low cabinets, drawer banks, plumbing runs, and battery infrastructure fill the space that code does not count as habitable. The central volume, where the ceiling reaches its full height, becomes the unobstructed living area. The end walls carry no structural load and can be full glazing, timber, or standard framing with windows. The A-frame is a structural geometry refined over centuries in the snowfields of Japan. It costs less to build, frames faster, and requires less ongoing maintenance than the rectangular box we live in right now. And if you want to see another structure that utilizes the geometry of the triangle to create some of the strongest structures known to man, then take a look at our video on the geodesic dome next.